Okay, in this question here, we're asked to find the volume of the largest right circular cone that can be inscribed in a sphere of radius 3. Okay, some key things here is we want the largest. So we're looking to optimize, and what are we looking to optimize? Alright, the volume of the largest right circular cone that can be inscribed in a sphere. So we know it's a sphere, and we know that we have a radius of 3 for the sphere. This is question 12 on page 220. Okay, so if we take a look at a picture of this, alright, here's our picture. Notice that here's our sphere, okay, and so it has a radius of 3. Okay, so this from here to here is 3. Right, here's our right circular cone, which we'll say has a radius of x. Okay, let's say that this height here is y. Okay, and so the height of the cone is 3 plus y, and of course what we have here is the radius is x. Right, now given that information, these are the things that we know. Alright, number one, we know the volume of a sphere is going to be 4/3 pi r cubed. Okay, we know the volume of a right circular cone is going to be, so let's call that S, and the cone is going to be 1/3 pi r squared h. Right, now this is the one we're wanting to maximize. Okay, so this one here, the sphere, alright, we know is fixed because it has a radius of 3. So we know its volume, alright, is fixed when it has a radius of 3. So the one we're looking at is the volume of the cone, which is 1/3 pi r squared h. So we've got two variables, r and h. Right, so let's have a look and see what we're going to do with that. Right, so here's our solution. Remember, we want to maximize the volume of the cylinder, of the cone, I should say. Okay, of the cone. So this is V equals 1/3 pi r squared h. Now, from our picture, we can see that the height of the cone is y plus 3. So here we first of all we have that h is equal to y plus 3. So that's the first thing. Right, secondly, if we look at the picture, right, we need the radius. So if you look at the radius, this is x. So x is the radius, and what is this radius going to be? Okay, so what are the relationships we've got here? Well, notice that we have a right triangle in terms of y and x. So we have x squared, which is the radius. Right, so let's put that down. R is equal to x, which is going to be equal to, if we use Pythagoras, alright, notice here, we have x squared plus y squared equals 9. Okay, so this means that if I want to find the radius, which is x in terms of y, I could write it as the square root of 9 minus y squared. So let's do that. So square root of 9 minus x squared. Right, so we have the relationships now, and so let's come back to the volume, and we see that the volume is equal therefore 1/3 pi r squared. Well, we're going to square this, so we'll get a 9 minus x squared, and h is y plus 3. Okay. Alright, so we currently have, alright, an expression for the volume in terms of y, which is the height of the cone. Now what we want to do is we want to maximize, okay, the volume. So to find an optimal point, we're looking for an extreme value for the function. So to do that, we're going to need to find the critical points, and so to do that we need the derivative. So I'm finding the derivative with respect to y, and this will be pi on 3 is a constant. Now let me just correct this. That should be a y. We've got this in terms of y. Okay, so make sure you make note of that. This was y squared. We had x is equal to the square root of 9 minus y squared. Alright, so notice here we have this is going to be a product rule, so the derivative of the first function here is going to be negative 2y multiplied by the second function plus 9 minus y squared. Okay, and we're going to need the derivative of y plus 3, which is 1. So I end up with pi on 3, and I'm going to have a negative 2y squared minus 6y plus 9 minus y squared. Alright, okay, now simplifying this, okay, this becomes, alright, let's see, we're going to have a negative 3y squared, we're going to have a 9, okay, and we're going to have, so let's do this, pi on 3, we're going to have a 9 minus 6y minus 3y squared. Okay. Okay, so that's what we have so far. Now, we want to optimize this, so we're going to need to find critical points, aren't we? So critical points occur, of course, whenever the first derivative is 0 or undefined. We can see here in this case that 9 minus 6y minus 3y squared is not undefined anywhere, so we just need to look for when this is going to be equal to 0. So dv on dy equals 0 when, okay, well, the pi on 3 doesn't count. Well, we'll put it in there just so you realise that we have this is equal to 0. Okay, so we don't need to worry about this. We can divide both sides by pi on 3. We can actually divide through by 3 as well and get 3 minus 2y minus y squared equals 0. And of course I think we can factor this, and it looks like we can factor it into let's see, we're going to have a 3, a 1, and we're going to have a y, and we're going to need a negative y, and it looks like we have a plus here. So let's make sure this works. No, I think we did have it the right way. So we're going to have a y minus 1 minus y and a 3 plus y. So we're going to have a 3 plus y minus 3y is minus 2y negative y squared. So we have it. Alright, so given that's the case, we can now look at so let's put this down, 3 plus y by y minus 1 minus y equals 0. So this implies that y is equal to negative 3 or y is equal to 1. Okay. Alright, so consequently we have a negative value here. Now what was y? If we come back to our picture, you see that y is this length here. Now it can't have a negative length, so particularly negative 3, this would be outside what's called the domain of the function. And you'll see from the picture here that the domain of the function must be that y is going to have to be less than 3 but greater than 0. Alright, so what we have here, we would have disregard this one, and we have y is equal to 1. So our critical point that of interest is y is equal to 1. Now we'd like to know, is this going to be a maximum? Well, of course, to do that we could always look at the second derivative. So you'll notice that the first derivative is equal to pi on 3 9 minus 6y minus 3y squared was what we got. And if I find the second derivative, pi on 3 stays, and I'm going to have, this will be 0 minus 6 minus 6y. Now when we test this, and this is the second derivative test, is when y is equal to 1, okay, we have d2v on dy squared is going to equal pi on 3 negative 6 subtract 6 by 1, so it's clearly going to be negative. So since we have the second derivative negative, right, then 2v on dy squared is less than 0, so we have a maximum at y equals 1. Right, so we've established that we're going to have a maximum volume, okay, at y is equal to 1. And what is that maximum volume? Alright, the maximum volume would be, and we always go back to the volume, remember, was 1/3 pi r squared h. Now we also had that h was equal to y plus 3. Alright, and so we have y is equal to 1, so h is equal to 4. Alright, and of course the radius alright, was given by the square root of 9 minus y squared, so this is going to be the square root of 8. Alright, so when we come to find the maximum volume, then we have 1/3 pi the square root of 8 squared by h, which is 4, and this comes out to be 1/3 pi by 8 by 4, which is 32 pi on 3, will be the maximum volume for a right cone that can be inscribed in this sphere of radius 3.